Hi guys, these are the notes for section 6.3, day 2. Section 6.3 is all about the properties of the trigonometric functions. Day 2 is going to concentrate on trigonometric identities. So if I gave you guys this expression, 2 times the quantity x plus 3, we could simplify that expression or rewrite it in an equivalent way by distributing the 2, and then you would get 2x plus 6. So this is what an identity is. It is a statement of equivalence. It is the way that you can rewrite an expression in a different but equivalent form. So whether I write it like this or like that, it's still equal. It means the same thing. Whatever number I plug in for x here, I will get the same answer for whatever I plug x in over here as well. So this is a statement of equality. It's a way to rewrite something in another form. I can rewrite this expression in an equivalent and different way, but they're still equal to one another. And that's what, the identities are going to be about. But we want to be able to apply them to the trigonometric functions, to sine, to cosine, to tangent, and whatnot. All right, so your notes look like this, okay? All right, so trigonometric identities. Trigonometric identities are statements or expressions of equivalence. They allow us to rewrite expressions in an equivalent way, or more importantly, they will allow us to rewrite one trig function in terms of another trig function. That's going to be the most important point that comes out of this, is that we're going to have a way to kind of, oh, you have tangent in the problem? I can rewrite that in terms of sine and cosine and whatnot. How we can get one trig function out of a problem and another trig function into the problem. All right, so you've already been working with some of what we call identities, statements of equivalence. We know that the cosecant of an angle is the reciprocal of sine. So we can rewrite that as 1 over the sine of angle theta. And that's a statement of equivalent. No matter what angle you plug in here or here, you're going to get the same answer. All right, your secant of angle theta, that's the reciprocal of cosine. So that's known as 1 over the cosine of angle theta. That's an identity. That's in a statement of equality. I can get secant out of the problem and cosine into the problem. All right, and then if you have the cotangent of angle theta, that is, by definition, it's the reciprocal of tangent, so it's 1 over the tangent. Okay, those are known as your reciprocal identities. We've already been working with them. But you also have your quotient identities. And these are important because I feel like we use them a lot. So remember, tangent first started by being the sine of angle theta divided by the cosine of angle theta. So if you have tangent in a problem, you can take tangent out and introduce a sine and cosine into that problem. If you have a sine over a cosine, you can take that out and introduce a tangent. They work both ways. They are equal to each other. All right. The cotangent of angle theta, also by definition, he is the reciprocal of tangent, which means he is then the cosine of angle theta divided by the sine of angle theta. So again, it's a way to get a cosine over a sine out and a cotangent in, or take a cotangent out of a problem and introduce a cosine and a sine. We can sub different trig functions in and out of a problem for each other. Those are what these are. They are statement of equalities, statement of equivalences. All right, so let's try an example. So example 1 says, given that the sine of angle theta is root 5 over 5, and the cosine of angle theta is 2 root 5 over 5, find the exact values of the 4 remaining trigonometric functions of theta using the identities. So again, method 1, because there's, again, a couple different ways you can do this problem. Method 1, they want you to use your identities. They want you to use what you know. So they want you to use all of these definitions that we just wrote up here. So guys, think about it. If they told you that the sine of angle theta is root 5 over 5, then we automatically know the cosecant of angle theta is his reciprocal. So technically it's 1 over root 5 over 5, but we can just take this and flip it over. It's 5 over root 5, right? And then I clean it up, and I'm going to get 5 root 5 over 5, which cancels, and then you're just left with root 5 as your cosecant of angle theta. All right? If they're going to give you the cosine of angle theta, then you automatically know that the secant of angle theta is his reciprocal. It's 1 over the cosine. So now we know automatically that the secant of angle theta is his reciprocal, 5 over 2 root 5. Okay, and we clean this up, times by root 5, and we're going to get 5 root 5 over, well, root 5 times root 5 is 5. 5 times 2 is 10. And then 5 over 10 reduces to root 5 over 2. And now you know the secant. So the only one we're left to find is the tangent and the cotangent. Well, remember, tangent, by definition, is the sine over the cosine. So I can just take the sine function, root 5 over 5, and put that over the cosine, which is 2 root 5 over 5. And now I just have to clean that complex fraction up. So I'm going to times by the denominator's reciprocal, 5 over 2 root 5, cancels all of that out. And then I'm going to times by 5 over 2 root 5. So now my 5s are going to cancel. My root 5s are going to cancel. I'm left with 1 over 2. I'm left with 1/2. So now you know the tangent of angle theta is 1/2, which means now the cotangent of angle theta is his reciprocal, 1 over the tangent. So it's 1 over 1/2, which is just going to be 2. And now you have found all the other trigonometric functions. Technically, as long as you know sine and cosine, there's really no trig function you can't find. There's no ratio you can't get if you know the sine ratio and the cosine ratio. You can build all of the other ones. All right? Now, another way to do this is just, guys, draw a right triangle. If you draw a right triangle, right? Give yourself one of the angles to work off of, theta. Think about it. They told you sine theta is root 5 over 5. That's O over H. So O would be root 5 and H would be 5. Now, even if they didn't tell you cosine, you could automatically find the third side by using Pythagorean theorem. A squared plus B squared equals C squared. And you could literally get your third side without even having to know another trig ratio. Or now you know cosine of angle theta is adjacent over hypotenuse. And since the H's are the same, 5, we can just use this as our adjacent side to root 5. All right, and then you can literally just build all of the other trig functions just by doing O over A, O over H, A over H, A over H, O over H, A over O. You can build all of the other trig functions just by using this right triangle. So I'm not going to write all those down because all the answers are over here, but you could use this picture now to get all of those ratios, and it would be the exact same thing, okay? All right. These are really, really important. We have the Pythagorean identities. See, there's lots of different identities that we have with the trig functions. We have our reciprocal ones, but again, they're kind of common sense because you've been working with these reciprocal ones all along. The quotient ones, you've been working with all along. When you were first taught sine and cotangent, tangent and cotangent, you were given these definitions. So these identities you have seen all along and you've always used them in trig. The Pythagorean identities come up a lot because, again, they're going to be able to help us get certain trig functions out of a problem and other trig functions in. So what are the Pythagorean identities? There's quite a few of them.